Hi, welcome to your flip video for 4.1. 4.1 is called Rational Numbers, Opposites, and Absolute Value, and they really grouped all three of these together because they're relatively easy ideas to work on individually, and wouldn't make sense to make a whole section for each one. So they kind of group them together. And this is really our introduction to topic 4, which is adding and subtracting rational numbers. Topic 5 is all about how to multiply and divide them. So that's why we're really grouping all this together, okay? So rational numbers, opposites, absolute value. In order to figure out what we're doing while all this, you need to know what a rational number is. So let's start with the most simple number possible, your natural numbers, all right? And these are also called your counting numbers. They might be referred to like that. Digits doesn't make a distinction about natural numbers for whatever odd reason, because digits sometimes makes weird decisions. But natural numbers are the natural numbers. And when I say natural numbers, like they occur in nature, they naturally happen. So these are the numbers that you would count, right? So you can have 1 thing, 2 things, 3 things, 4 things, 5 things, right? All the way up to whenever you're done counting. So it goes all the way to infinity, technically, all right? So natural numbers are all the things that you can count on your fingers, basically, all right? Now, let's get one step bigger than natural numbers. This is where digits jumps in. These are our whole numbers, okay? So the only difference between the whole numbers and the natural numbers is that whole numbers also include 0. So it starts at 0, 0, 1, 2, 3, 4, and all the way on up to infinity, okay? So you could say that the whole numbers is really just the natural numbers plus 0. All right, that's the only difference. All right, so if a number is a natural number, it has to be a whole number. And notice how I'm making these circles one around each other. It's kind of like a Venn diagram, but one circle is completely inside the other. So all the natural numbers is inside, or all the natural numbers are inside the whole numbers. So if a number is a natural number, it has to be a whole number. Now you could have a whole number that's not a natural number, right? That'd be a little. Like, let's say you have that, x, whatever, that represents some point on here. That'd be a number that is a whole number. It's in the whole number circle, but it's not in the natural number circle, all right? And we now know that the only difference between whole numbers and natural numbers is 0, so this x would have to be 0, okay? So you can always figure out what type of number a number is based off where it's located in these overlapping kind of Venn diagram type things, okay? If we go one step further than whole numbers, well, you have 0, 1, 2, 3, 4, all the way up to infinity. How can you build upon that? Well, you can take the integers, and integers are negatives plus the whole numbers, right? It's 0, and then up to infinity, and then 0 down to infinity. So 0 is like your middle point. So we could say our integers are the negative numbers plus the whole numbers, all right? So notice how they keeps building upon each other, okay? So same thing, if a number is an integer, it could not be a whole number, and it could not be a natural number, right? If you had a little, like -3, right? -3 is not a whole number, it's not a natural number, but it is an integer, okay? But notice still, natural numbers and whole numbers are inside integers, so all the natural numbers and all the whole numbers are all integers, okay? So let's keep going. One thing bigger than integers, rational numbers, okay? And this is where digits caps it, because I think they do it, because rational numbers is what we're looking at in topics 4 and 5, but it keeps going, and I'm going to put this picture, I'm going to try and line up rational numbers on top of each other, all right? So if you look in the bottom left-hand corner over here, that's the whole circle, the ones that I made, the white, yellow, green, and blue circles, natural, whole, integers, and rational numbers, that's all there, okay? And so all of these, it kind of looks like ripples in a pond. This whole section, rational numbers, fits into a group of numbers called real numbers. And in the group of real numbers, you have our rational numbers, and those are the numbers we're going to talk about. But we also have irrational numbers, which we're not even going to touch, but I want you to know that they're there. Now, ironically enough, it even gets bigger than this. Real numbers, there's another grouping of numbers on top of this. You also have imaginary and complex numbers. You probably won't even see those in high school, but I just want you to know that there are numbers that don't fit nice and neatly into these categories, but I wanted you to know that they were there, okay? But this is what we're talking about, okay? So you can have rational numbers so all the natural numbers, all the whole numbers, all the integers are all types of rational numbers, but there are other rational numbers that aren't natural numbers or whole numbers or integers, okay? So let's look to what a definition of a rational number is. Well, a rational number is a number that can be written in the form a over b or negative a over b, okay? So we have a little asterisk here. There are conditions on what a and b can be. So first rule, a and b need to be whole numbers, okay? The second rule is that b cannot be 0. Okay, so some examples of rational numbers, 1/2, right? I can write that as a over b. A is a whole number, b is a whole number, b is not 0. Okay, if you are confused as to why b can't be 0 but a could be 0, check out this video and it'll walk you through what that is. You're not required to watch it, but it's cool. All right, so 1/2 is an example. Negative 5/6, right? That's a over b. A and b are both whole numbers. B is not equal to 0. It's in the form negative a over b. So we can keep going a little bit faster. 1,123 over a million is a rational number. 9.09, right? You could write that as, that 9.09 is the same thing as 9 plus 9 over 100. So if you combine these two, 9 is the same thing as 900 over 100. So 900 over 100 plus 9 over 100. So 9.09 is the same thing as 909 over 100. Okay? So I can write it in a over b. Just because it's not written in a or b doesn't make it not a rational number. The definition says it can be written, okay? So it means that you have the ability to write it in a over b, not necessarily that when it's given to you, it is an already a over b or negative a over b. All right, so we have 9.9, we have negative 6.35, same thing. I'll walk you through those steps. Let's just keep going, all right? So over here, let's put some numbers. You might be thinking in your head, well, aren't all numbers rational numbers then? How could you possibly have a number that's not a fraction or a negative fraction or a positive whole number or negative or decimals? And to be rather frank with you, you've probably only been exposed to rational numbers throughout your math career. So I'll give you a couple of examples. Pi, which is 3.14159, and then it keeps going on and on and on and on forever, but there's no pattern. There's no way to write pi as a over b or negative a over b, so pi is an irrational number. Some other examples is the square root of 2, which is roughly 1.4, but it's, again, a decimal that keeps on going forever in no pattern. It just keeps going, all right? The square root of -1, for those of you who know this, you cannot take the square root of a negative number, so this is actually an example of an imaginary number. Once again, don't worry about that, but it's something to keep in the back of your head, a preview of what you're going to see in high school and college, all right? This is the symbol for the golden ratio. It is a non-repeating, non-ending decimal, so again, something that you might see in college or beyond. And then E, if you ever notice on your scientific calculator, there's an E button, and then it asks you for an exponent. Without going too deeply into what E is, it is, again, a non-repeating, so there's no pattern, and non-terminating, so that doesn't end number, all right? So there aren't a lot of examples of there are lots of examples of irrational numbers, but no examples that you have probably used before in your math career, all right? So the next part is absolute value, and the definition of absolute value is the distance a number is from 0 on the number line. So I think the easiest way to explain this is just to look at it. The absolute value symbols are just two vertical lines around the number. So in this example, you have two vertical lines around x, so this would be read as the absolute value of x, okay? I make my absolute value marks a little bit taller than my ones. If you have a number, the number 1 inside absolute value, I would suggest making your ones look like this instead of just a line, because then this kind of like, what is that, 101? Is that the absolute value of 1? It gets a little confusing if you aren't super clear. So you might want to get in the habit of making your ones look a little fancier. But let's look at a number line. So here I have a number line 0, 5, 10, 15, negative 5, negative 10, negative 15. And let's figure out the absolute value of 10. Well, 10 is right there. And how far is 10 away from 0? Well, it's 10 little jumps away from 0. It's 10 one spaces away from 0. That's why it has the value of 10. But the absolute value of 10, we're just going to count the number of jumps, the number of 1 jumps, how many spaces it is away. So absolute value of 10 is 10, all right? So the absolute value is the distance, how far away, the distance. And remember from class, that distance can never be negative. So what happens if you take the absolute value of a negative number? Well, negative 10's right there. How far away is negative 10 from 0? Well, it's also 10 spots away, all right? So same idea. You can never move in a negative direction. You can't have a negative distance, okay? So the last part of absolute value is the absolute value of opposites, and I picked 10 and negative 10 on purpose because they're examples of opposites, all right? So here are some examples. You have 2, negative 3 and 3, 5 over 4, and negative 5 over 4, all right? So the opposites are just a number and then the negative version of that number. So if you take the original number and multiply it by negative 1, you get the opposite, okay? So x and negative x, okay? So the absolute value of opposites have the same value. The absolute value of 10 and the absolute value of negative 10 is both 10, all right? The absolute value of 15 is equal to the absolute value of negative 15 because they're opposite values, okay? So negative 10, absolute value of negative 10 is equal to absolute value of 10. 10 is equal to 10. Good. All right, so here are some problems you'd see from your homework. Determine whether the given number belongs in each set, and you have negative 27, all right? So you have to do some thinking back. Once again, they don't include the counting numbers or the whole numbers, so you gotta do some thinking here. Whole numbers, 0, 1, 2, 3, 4, is negative 27 part of that category? Well, no, it's not. So we can get rid of that, all right? Well, is it an integer? Well, the integers is all the negative numbers, 0, and all the positive numbers. Well, negative 27 is a whole negative number, so yeah, it's an integer. And we know that integers fit inside the category of rational numbers, so if it's an integer, it has to be a rational number, okay? Here's one from your homework. Which of these situations can be represented by the opposite of 68? Use paper and pencil. Describe 2 situations that can be represented by the opposite of 68. So we're going to skip that second part, but the opposite of 68, well, let's look at these scenarios. A book was 68 pages shorter than you expected. Well, shorter means going down, so the opposite of 68 is negative 68, and if you're going down, negative 68, yeah, that's negative 68. That's the opposite of 68, all right? Andrew spent $68. Well, if you spend $68, what's happening to the amount of money? It's going down. So the opposite of 68 is going down 68. Okay, so yeah, that's also negative 68. The temperature was 68 degrees. Well, there's no change here at all, so this can't be negative 68. That just is regular 68. You could even say it's plus 68 because 68 degrees above 0, because we use 0. Not really in Fahrenheit, more in Celsius. 0 is more of a benchmark, but it's still an idea in Fahrenheit. 0 is nothing monumental, though. In Celsius, at 0 degrees, water freezes. At 0 degrees in Fahrenheit, water is already frozen at 32, so it's just really cold. Jennifer sold 68 apples. Well, if you sold something, it goes down. So her number of apples decreased by 68. Negative 68 is the opposite of 68. So we have options 1, 2, and 4, but not 3. Okay? If you have any questions, let me know. Most of you seem to be getting this pretty good.